Hello, good afternoon, Chaitanya.
Good afternoon, sir.
Good afternoon. You are the only member as of now, before 15. So let's wait for another 3-4 minutes. Okay?
Okay, sir.
Right. Almost candidate has joined. But anyway, you are only two in number. So let's just wait for another few minutes. Okay, welcoming to contact session 7. No improvement except one more candidate. So as of now, there are three: Chaitanya, Asta, Samreen, Fatima. And for Samreen Fatima got disconnected. So week after week, the attendance is becoming so weak. Anyway, at least one or two are there to listen. And it so happened last week there was a lone member. but she was there throughout the proceedings of 2 hours, the session. Hope you will also be there. Okay, so with this, so today's the topic is going to be solving a system of linear equations by Gauss elimination method. Now, without knowing the nomenclature of the method that you are deploying, you might have come across, at least you must have heard about, finally, back substitution. So initially, so it has got the two important steps, namely elimination and then back substitution. So you may not have come across the term elimination here exactly, but you would have done in finding the rank of a matrix or ranks of augmented matrix whenever you want to test a given system of equations to be consistent or otherwise. You might have done elementary row operations. Thereby, you are making the given matrix, reducing it into its echelon form. So in that process, you might have done the elements below the principal diagonal or leading diagonal elements to be zero, so that you are doing actually a kind of elimination. And then you are getting reduced to, so to find the non-zero number of non-zero rows to get the rank of the matrix and rank of the augmented matrix, so that etc. But now that you have Ax equal to B, a non-homogeneous system of linear equations. And of course, in general, you will be having 3 equations in 3 unknowns. And sometimes you may also have 4 equations in 4 unknowns, rarely. But anyway, the idea is the same. So you will be reducing it to the echelon form, its echelon form, preferably upper triangular form. So, and in that process, you are doing elementary row operations, and then you are finally left with, supposing it is a 3 by 3 matrix, the last column, third row, with the corresponding constant in the column matrix on the augmented matrix. So you have, that is coefficient of Z. So that Z equal to that constant, so that you are getting Z value. Then go to the second row, back substitution. Now you will only have two on the left hand side, that is coefficient of Y and coefficient of Z, and then equal to the constant. So you are supplying the value of Z, which you have already got from the previous step. Now that you are able to get the value of Y. So having come to know the values of Y and Z, you go to the first row where you have the 3 coefficients of X, Y, Z, where you will substitute values for Y and Z and get the value of X. This is called back substitution method after doing the elimination. And this elimination is named after the famous mathematician Gauss. And therefore, it is called a Gauss elimination method. So this is in general. After doing this one, here we are laying a special emphasis on doing a kind of pivoting. That plays a significant role. You know what is meant to be a pivot, isn't it? Something on which something is rotating, isn't it? So pivot. So here pivot means that particular element plays a vital role. So that the element that is available from that particular column is called a pivot column. Which is pivot column? Which is pivot element? And how do we go about as a special particular case of your Gauss elimination method, preferably called a partial pivoting method. So all those things we will discuss in detail. Right. As I just mentioned in my introductory remark, the agenda is in general, that is the method that we are going to adopt to solve a given system of linear equations called a Gauss elimination method. Methodology, partial pivoting, which is very important. etc. Okay. So again, as you are much familiar with, but still, as we are going to find the solution of linear equations, a system of linear equations. And we will have to again start with a recap that how do we write in general. A linear system of m equations in n unknowns, say x1, x2, xn, is a set of equations of the form, you know very well, a11 x1 plus a12 x2 plus etc. plus a1n xn equal to b1. A21 x1 plus A22 x2 plus etc. plus A2n xn equal to B2, etc. etc. AM1 x1 plus AM2 x2 plus etc. plus AMN xn equal to BM. Thus, we are having M equations in N unknowns. And you know very well, this set of system of M equations can be written as a matrix equation. On the left hand side, a product of A and X, and right hand side B. A is matrix of coefficients A11, A12, etc. A1n, A21, etc. A2n, etc. AM1, etc. AMN. So that it's going to be an M by N matrix. And X is nothing but your column matrix, or rather column vector having n components x1, x2, etc. xn. If the system has got three equations in three unknowns, then your A will be of order 3 by 3, and your X, the column vector, will be having only three components x1, x2, x3. In practice, you will be having at the most three, at maximum four, but in particular in general three. Okay, right. So next on the right hand side, we'll be having constants. So the system is called linear because you know very well, each of the variables is having maximum power of 1. A11, A2, etc., A1M are given numbers called the coefficients of the system, you know very well. So that is going to form the entries of your matrix capital A to be called matrix of coefficients. B1, B2, extra Bm on the right are also constants. Okay. If all the Bj's are 0, then the system is called a homogeneous system. Otherwise, called a non-homogeneous system, which you, of course, you are already familiar with. Now, so this is what exactly we have been talking about. From the definition of matrix multiplication, we see that the m equations of one that we have seen may be written as a single vector equation, Ax equal to B, where the coefficient matrix A, which we normally denoted by Aij, is the m by n matrix. X and B are column vectors, which I just have mentioned. So capital A, matrix of coefficients, m by n matrix, if there are m rows and n columns, and X, according to this description, that the system one has got m equations in n unknowns. Therefore, you have the constant vector or column vector having n components x1, x2, etc., xn, and B, the column vector again having only constants b1, b2, etc., bm. Now look at this symbol, and this of course there is a symbol overhead A, something like a small wave-like symbol, small wave-like symbol, small wave-like symbol, not this one, a small wave-like symbol, and of course that is being described as, that is being called as tilde. But anyway, don't bother about all those things. You can just take the matrix of coefficients A, and then you can make a vertical line, either dotted line or straight line itself, just to have a demarcation between your A and the column vectors, that is constant vectors, constant vector. So you can have A comma B. Actually, instead of writing just A tilde, you can easily write better. That's what we have been describing all along. So you can write it here, capital A comma capital B, capital B or small b, whatever you are taking. See, I have mentioned in the beginning itself that capital X, if you are putting, okay, you can have capital X, or you can have small x a bold face, so as to mean it's a vector. Similarly, small b bold face to mean a vector. Otherwise, if you take it as a column matrix, that way you can take it as capital B, nothing wrong. Or you can take capital A, comma small b, where small b must be lowercase, and I mean b is lowercase but bold face to mean vector. So this shows you clearly that you are having A here, you are having B here, whatever small b or capital B, it doesn't make a difference. So this is called your augmented matrix of the system of equations 1. Instead of using the tilde, you can be clear, you can be explicit, writing A, comma B. A solution of the system of equations is a set of numbers x1, x2, x2, xn that satisfies all the m equations. Very well, then only it becomes a solution. A solution vector of 1 is a vector x. So altogether, when you take them as the components x1, x2, xn, and then you have the column vector as a whole, it's called a solution vector, whose components form solution of 1. If the system 1 is homogeneous, it is always has at least the trivial solution. So if the right hand side constants are all zeros, the system is then called as a homogeneous system. So in which case, naturally, there is definitely one solution at least, and that is trivial solution, which means x1 equal to x2 equal to etc. xn equal to 0. Okay. But in general, by to find a solution, we are always expected to find a non-zero solution, not non-trivial solution. Okay, not trivial solution, non-trivial solution. Okay, you just look at these three cases, because when you solve a system of linear equations, you may encounter having that system to have only unique solution, infinitely many solutions or no solution. So again, when will you have precisely or exactly one solution? When will you have infinitely many solutions? When will you have no solution? So you can easily understand. So ordinarily, by looking at geometrical way of, so here you have an equation. If you take the first graph, x1 plus x2 equal to 1, 2x1 plus x2 equal to minus x2 equal to 0. x1 plus x2 equal to 1. So you are plotting the equation x1 plus x2 equal to 1, 2x1 minus x2 equal to 0. So here, if you ordinarily solve this one, a plus x2 minus x2 get cancelled. You have 3x1 equal to 1. So x1 equal to 1 by 3. So by at 1 by 3, you have 1 by 3. And you are finding, if you substitute for x1 equal to 1 by 3, you get x2 equal to 2 by 3. Therefore, you are having an intersection of these two straight lines at 1 by 3, 2 by 3. That is the only solution. That is the unique solution. So when you take the second one, you have x1 plus x2 equal to 1, 2x1 plus 2x2 equal to 2. So when you look at the second equation is nothing but 2 times x1 plus x2 equal to 1. They are one and the same except the multiple 2. So therefore, you have two parallel lines. So when you have an equation and another equation is just a multiple of the previous one, and any number of equations like that, if you write, you only have parallel lines. So you don't have any intersection at all. So you have here, what is happening actually, if you are, there are two unknowns, and then you have only one equation, because though there is another equation, it is nothing but the first equation 2 times. Is it right? And therefore, what's happening, if you have to have one of the two components to be assumed, then you can find the other one. So there is only one equation, but there are two unknowns, in which case you need to assume value of one of the two variables so that you get the other one. So that what will happen, depending upon the assumption of the variable that you will be able to generate as many solutions as possible. For example, if you take x2 is equal to 0, then you can have x1 equal to 1. Suppose x2 equal to 1, then x1 will be 0. Suppose x2 is equal to 1 by 3, then x1 will be. So depending upon the value of x2, you will get x1 or other way around. And therefore here you will get infinitely many solutions. Remember, if you are having two equations apparently, but one is multiple of the other, or one is in fact one and the same they are. 2x1 plus 2x2 equal to 2 means it is 2 times x1 plus x2 equal to 1. Therefore, equations 1 and 2 are the same. Therefore, when there are two unknowns but one equation, you will have to have substitute an assumption of one and get the other one. So the value of getting the second variable is purely depending on the assumption of the first one. And therefore, as long as you assume the value of any one of them, you will be able to generate here infinitely many solutions. Coming to the last one here, of course, here actually it's not parallel here in the sense when you go to the last one, you just see that x1 plus x2 equal to 1 and x1 plus x2 equal to 0. So here actually you have a parallel equation in the sense they never meet. So here this equation x1 plus x2 equal to 0 passing through the origin, and here it is at x1 equal to 1. You have x1 plus x2 equal to 1. So you got this is something like your slope intercept form. Anyway, so here what's happening if you do by usual way of elimination, whenever you have two equations in two unknowns, if you subtract the second equation from the first one, you get x2 minus x2, x2 gets cancelled. The same way, x1 will also get cancelled, isn't it? Therefore, there are no unknowns at all when you solve these two equations. That means you are not able to find the values of x1 and x2, which means this set of equations has no solution. Thus, for any set of equations, you can have unique solution, infinitely many solutions, and no solution. So with this background, if you go back to the ideas that you have after finding the rank of a given matrix and then finding ranks of the matrix and the augmented matrix AB, you are able to say that if rank of A equal to rank of AB equal to, if they are equal, first of all, you will be able to say that the system is consistent. But again, if then the system is consistent, means it has solution. So what type of solution, whether it has a unique solution or infinitely many solutions, depending upon the condition. Well, the ranks are equal, but if it is equal to n, suppose you talk about a system of m equations in n unknowns in general, then rank of A equal to rank of AB equal to n number of unknowns. Here, the system is consistent, and then there is therefore a solution which is unique. If the number of unknowns, the ranks are equal, consistent, and further it is equal to the number of unknowns, means the system is consistent to have a unique solution. Now again, rank of A equal to rank of AB, system is consistent, it has solution, but less than n. For example, you are considering a set of a system of three linear equations, and then you are finding out the rank of A equal to rank of AB equal to 2. System is consistent, but then it is less than 2, is less than number of unknowns 3. In which case, the system is though consistent, it has infinitely many solutions. And finally, if rank of A not equal to rank of AB, we can say system is inconsistent, which means there is no solution. Are you able to follow this? Chaitanya?
Yes, sir.
Hello? Yes, clear? Okay.
Yes.
Therefore, so the system is, so the very important thing is that you are going to determine whether a system is consistent or not, which you of course already seen in the, I think second or third sessions. And then you have also come to know that you will be comparing with the number of unknowns. Now that a time has come to exactly see that, of course, already I had indicated this, but now you are again recapping it in the context of finding system, so solutions by Gauss elimination. Okay. So here, whenever you have number of rank of A equal to rank of AB equal to the number of unknowns, the system is consistent and has a unique solution. The system is consistent, but less than the number of unknowns. System has solution, but it is many. And if the ranks are not equal, you will declare that the system is inconsistent, which means there is no solution. So these are the simple graphical representations to represent our idea. So a linear system is called overdetermined if it has more equations than unknowns. Underdetermined if it has fewer equations than unknowns. Furthermore, a system is called consistent if it has at least one solution. Inconsistent, it has no solutions at all. It is a converse. System is inconsistent, it has no solutions, and vice versa. Same thing, consistent, it has at least one solution. Already you are familiar with, we have done enough in elementary row operations to find the ranks and to finalize the consistency or otherwise of the system of equations given. So once again, let's just go back because these are all going to be part of your methodology when you are going to take up this Gauss elimination method to solve. Elementary operations for equations, interchange of two equations is a kind of an elementary operation. Addition of a constant multiple of one equation to another equation. You will multiply an equation by a constant multiple and you can add it to another one. So these are all we have seen, isn't that? Multiplication of an equation by a non-zero constant. Okay. Then row equivalent systems. Row equivalent linear systems have the same set of solutions. Clearly, the interchange of two equations does not alter the solution set. So that we could have seen. These things will be useful for you. I think would have done it in your MCQ also in first quiz. That if you interchange, especially in your here we say interchange of two equations does not alter the solution set, and you might have seen, you might have experienced in determinant expansion of determinants by interchanging. What will happen? It will only change, make a change in sign. So like that, you have some properties which you have already seen as far as determinants were concerned. So here, coming to the solution of the set of equations, by interchanging the two equations, it will not alter the solution set. Neither does the addition, because we can undo it by a corresponding subtraction. Similarly, for the multiplication, which we can undo by multiplying the new equation by 1 by c, whenever c not equal to 0, producing the original equation. So here what we are trying to say, so you know very well when you do addition, definitely it will not alter. Like interchange of two equations will not alter the solution set. Addition, because you can undo by subtraction. Multiplication, you can undo by division. And therefore, with all these properties are in place, any elementary row operation that we do will not alter the solution. Gauss elimination and back substitution. So when you are solving a system of linear equations by Gauss elimination, it involves these two steps predominantly, namely elimination and back substitution. Okay. We know very well upper triangular form. So what do we do before we go for when we do elimination? What do you mean by that? What we are actually obtaining by elementary row operations, the echelon, which means triangular form. And of course, we have been practically uniformly doing it to reduce it to echelon upper triangular form. Okay, but we might be able to recapitulate if you have been really following that whenever you wanted to find inverse of a given square matrix by Gauss-Jordan method, starting with the augmented matrix A, I, the matrix that is given, augmented with the I unit matrix, and making elementary row operations once to have it reduced to a upper triangular form, and again to make it to lower triangular form, so that you only have on the left now 1 0 0 0 1 0 0 0 1. Suppose your matrix is of order 3 by 3, and the right hand side a matrix, and that is going to be the required inverse matrix, isn't it the same? So what does this mean? You can have both upper triangular or lower triangular, but let us uniformly do low upper triangular and also do uniformly row elementary operations, which will be easy for operation. So upper triangular means that all the non-zero entries of the corresponding coefficient matrix lie above the diagonal and principal diagonal and form an upside down 90-degree triangle. Okay, you know very well. Back substitution. Solve the system by back substitution. Solve the system by back substitution. You just see what it exactly it means. I've already explained, but you need to see for believing. Okay. Consider this Gauss elimination method, which is a method of solving a linear system as before, consisting of m equations and nodes in general, by transforming the augmented matrix AB into an upper triangular form. So your AB gets transformed into this way. Just look at the second C11, C12, etc., C1n. You know very well. The first row will be there as it is. As it is in the sense, of course, it will undergo some transformations, but you will have all the entries in the first row. In the second row, first column will be 0, will be made to be 0, and you have C22, etc., C2n, some D2, etc., etc. And in the last row, you have, except the last column, all other elements are zeros, and you have the constant in the right hand side, say dm. So this is what exactly we are getting or reducing the given augmented matrix, the augmented matrix that we write from the given set of equations into its corresponding echelon form, preferably upper triangular matrix. And this is called exactly what we do here by performing elementary row operations, that is performing operations of addition or multiplying a particular row by a common multiple and then adding it to, or subtracting one row from the other. These are all forming part of your elementary row operations with an aim of what's happening actually here by this kind of row elementary operations. What is happening actually? We are eliminating coefficients of eliminating x, y, z by in the echelon form. So here what's happening, therefore, the elimination process is also called the forward elimination method. See, in fact, you are starting from row 1 being fixed, and then you are applying, acting on row 2 or performing elementary operation of R2 on R1, of R3 on R1. First set. Supposing we start with the basic practical 3 by 3. Then in the second set, you will do one more set of elementary row operation of R3 with R2 fixed now. Therefore, this is a kind of forward elimination. By backward substitution, this is forward elimination, and by backward substitution, the solution of the system is obtained. Again, so when you just look at, this is what exactly I was talking about. Example. So what do you mean by here backward substitution? So you know very well by we have made it to be in the echelon form, preferably upper triangular form, which we are familiar with. So now that how it gets reduced, what is that? Now that we have eliminated here some of them, so that these are all zeros, so that you have only the principal diagonal elements above which you are having non-zero entries, and then all of them below are zeros. So now that how do we go for back substitution method? Remember, this is this coefficient of x, this column coefficient of y, this column coefficient of this column coefficient of x1, these components are coefficients of x2, etc., coefficients of xn. These are constants. So here, so you have all the entries in your last column. So here, what's happening here? This is coefficient of your xn. So that number into xn you will write. That constant into xn equal to your dm. So that you are getting xn. You go to the previous one back. You get x minus, you will have two terms here. Now, n minus 1th column, nth column. You will have definitely two terms, isn't it? Supposing you just imagine to be 3 by 3. So you will have, suppose this is 3 by 3, just to have to have a clear understanding, easy understanding. So you will have here z or x3. This constant into x3 is this much, therefore x3 is equal to. So in the here in the second row, you will have this into x2 plus this into x3 equal to this much. Substituting for x3, you will be able to get x2. Now that in the first row, you got this into x1, this into x2, this into x3 equal to this one. Already you know values of x3 and x2. So by substitution, you get value of x1. And this is what we mean by backward substitution. Okay. Look at it. So if you really just want to express, how does again this augmented matrix look? Suppose here are a system of 4 linear non-homogeneous equations of the form a11x1 plus a12x2 plus etc. or plus a13x3 plus a14x4 equal to p1. Similarly, a21 etc. a41x1 plus a42x2 plus a43x3 plus a44x4 equal to p4. So this system of non-homogeneous linear equations can be written as a vector equation, of course, with matrix A or matrix product, matrix multiplication on the left-hand side. That is, you have AX is equal to B. So that we now write only the augmented matrix, only augmented matrix. Okay. So you have A, B will be looking like this, isn't that? That is coefficients of x1, coefficients of x2, coefficients of x3, coefficients of x4. That's why it's called a matrix of coefficients or coefficient matrix. These are constants. So you have a dotted line. So just to make a demarcation, a separation between the coefficients of unknowns and the few constants. Okay. Now, first equation is pivot equation. Look at A11 is pivot equation. Of course, pivot element, not equation. Here, pivot element. So this is your pivot element. I just. So is your pivot element. That is from where you are starting. Because you are going to eliminate the other coefficients of x1 from the first column. Also from the second column and then third column and then fourth column, so that you will make it as a upper triangular form. You will have only A11, A22, A33, A44. Beneath that, you will have zeros by doing elementary row operations. So what is F21? That is F21 means you will be getting A21 divided by A11. And then, so you are making some elementary row operation. That's what it shows here. And then you are making appropriate subtraction or addition to so as to make these values to be zeros, isn't it? So in order to make them, it is just written here. So if you just look at F21, F31, F1, you may not be able to understand. When you really practically do the problem, you'll be able to understand easily. Okay. So the first equation is pivot equation. Actually, pivot column, it should be called I would suggest this should be called a pivot column. So this that better you can take pivot column. Because column wise we are bringing in the pivots. The elements upon which we are fixing so that you are reducing into echelon form. So such of those elements which are responsible, which are important, which on which we rely upon are here pivot elements. So naturally we will start with the first column, then second column, then third column, fourth column, and so on. Okay. So pivot column, let us say first column is the pivot column and the first row, first column element is your pivot element. But we are going to have some more conditions imposed on getting this pivot element from the first column, but not exactly necessarily to be from the first row itself. We are going to impose some condition when we take it up as a special case of partial pivoting, and that is going to play a vital role. In fact, according to your scope, you are expected to use that partial pivoting technique to solve by Gauss elimination method, because these are all otherwise becomes ordinary. Okay, right. Let's see. First, let us do ordinarily, and then we go for the partial pivoting. So like that. So you know very well. So we just make this. So A21 by A11, sum F21. So what do we do? Equation 2 minus F21 into 1. You are getting 2 minus F21 into 1, 0. Then 3, my third row from third row minus F31 into 1, first equation. So all these things are there, but this will not definitely be helpful to you if you just read it as it is. What exactly you will be doing? You are doing element first column elements except the first row as of now to start with, as we are going in the forward direction called the forward elimination, making them all zeros. Then except second row, first column, second column, first row, second row. Then you will be making zeros. Then you will be making third row. Then keeping fourth column, third column, fourth row becoming zero, and like that. And therefore, you have to look at. So next, you are making zeros like this, isn't it? So F43 is your F43 dash, but divided by A33 dash, last one. Upper triangular matrix, 4 minus F43 into 3, all those things okay. So theoretically, you will not be able to. The same idea, but okay. So what's happening now? We are able to reduce the given augmented matrix into its echelon form, upper triangular form, preferably, of the form A11, A12, A13, A14, B1. The first row, after having undergone some changes, if any, will be there. But all the entries will be there without making them to zeros. But from the second row onwards, you have 0. Here you have some changes, isn't it? A22 dash, A23 dash, A24 dash, B2 dash. Some change in it, transformed. Then you have 0, 0, A33 double dash, and another transformation. A34 double dash, B3 double dash. Another transformation, 0, 0, 0, A44 some triple dash, B4 some triple dash. So that you have a echelon form, upper triangular form, and then you are going to have back substitution. So now what is back substitution? Elimination is done. Gauss elimination. So what is back substitution? As I already mentioned, A4 4M 3 dash into X4 equal to B4 3 dash. A33 dash double dash into X3 plus A34 double dash into X4 equal to B3 2 dash, and so on. So this is what we mean by back substitution. Look at it. So what is X4? This B4 3 dash divided by A44 3 dash straight. Then going back, A33 you need to find A33, you need to find now X3. So X3 will be V3 dash minus, first you will have A34 dash into X4, isn't that? This minus this divided by this coefficient A33 dash, A33 double dash. Next you will have X2, you will have 3 terms here. Then you will have 4 terms here. So this is what exactly we mean by back substitution, like that. With the condition that all those denominators you are going to divide by will be non-zeros. So this is what again explained here, the same thing. Now, it's a very simple example of solving a 2 by 2, a system of two linear equations. Solve the following linear system of equations by Gauss elimination method. 2x1 plus 5x2 equal to 2, minus 4x1 plus 3x2 equal to minus 30. First thing is that as you are familiar with solving a system of two equations in two unknowns ordinarily by elimination, in the sense you are multiplying by a common constant of the first equation and by the second equation. Suppose you multiply throughout by 3, multiply throughout by 5, so that you make 15x2. This is 15x2. Then subtract. When you subtract this, whole of the second equation is to be subtracted, so that you will have some value of x1 here constant like that. Don't do that way. Okay, that is ordinary way of solving system of two equations in two unknowns by elimination. Of course, that is also elimination. Suppose you have same coefficients like here 5x2, here also 5x2, you can subtract this term to cancel these two, so that x2 is eliminated. But that by elimination we don't mean that. So if you do the examination by that kind of elimination, that is not correct. Okay, marks will not be given. But then you are supposed to do by Gauss elimination method. Definitely that is your cup of tea. Therefore, you have to go by this method of elimination, then back substitution. So write the augmented matrix 2, 5, minus 4, 3, 2, minus 30. You may ask one question. Here there is no demarcating line, there is no separation. Do we need to write or not? It's better to write. Otherwise, sometimes you may go wrong with thinking that it is some 2 by 3, something like that. So it is augmented matrix, and always better you give name. You are given system of equations. You should write let A is equal to 2, 5, minus 4, 3, and B equal to column vector 2, 30. Therefore, augmented matrix A comma B equal to, better you write. Okay, and then make the, so here you write into augmented matrix capital A vector B so bold it being a vector. Okay, this is equal to, here better you make a demarcation. So this only now gives a clear picture of your augmented matrix. Okay. Here it is not like where better for real numbers or something like that. Not to have two lines. It is to be just a bold. Okay. Right. So next, this is equal to. This is equal to. So what do you do? You have only two rows now, isn't it? So this must be made 0. So which is the pivot column now? First column is your pivot column, and this is your pivot element. Of course, this pivot and pivoting, especially partial pivoting, we are going to take it up in a slightly different manner. So here, as of now, you just try to understand that it's just going to be elimination. So elimination means here you don't bother much about the pivoting, all those things. You have to make this element first row, first column, second element to become 0. You only think of now reducing it to echelon form. So here, the being a 2 by 2, this is the only element that you are going to make it 0. How will you make it 0? You have minus 4. This should become 0, isn't it? This should become 0. And this operation is to be performed against your fixed R1. Because R1, R2 junction, you are having the pivot element, isn't it? So that should not be touched. That should be fixed. That should be the foundation. So minus 4 you have, you just only concentrate on only one element which is to be made 0. That is minus 4 against the corresponding element in the first row. That is 2. So how do you get 0? Keep R2 as it is. Go to R1. R1 stands for first row. R2 stands for second row, isn't it? So 2 times R1, that is 2 into 2 plus minus 4, or minus 4 plus 2 into 2 will make it 0. So when you just make it 0, you are doing the computation of minus 4 plus 2 into 2. But what does it mean? R2 elements are to be kept as they are, plus 2 times R1 elements are to be 10. So you just look at here, that is what. So here you have to write R1 is R1. So you don't need to write, but I would suggest if you write that way, I have written that way in the examples. I have taken such type of examples where everything is clearly written. Now, this is R1. I will write R1. I think you must have studied in school days this way of writing. Put an arrow mark. Means R1 is R1 itself. This is the right way of writing. And then, of course, here you can write this way R row 2 plus 2 times R1. Or if you want to follow this notation, this is R2 means row 2 means capital R suffix 2 arithmetic operation plus 2 times, so 2 into R1. So what's the meaning? Minus 4 plus 2 into 2, minus 4 plus 4, 0. And it is to be done throughout second row. So here 13 plus 2 into 5. Sorry, here 3 plus 2 into 5. 3 plus 10, 13. Here minus 30 plus 2 into 2, minus 30 plus 4, minus 26. That's all. Being 2 by 2 is so simple, but this is what we mean by row elementary operation and elimination. Okay, that's all. No more elementary operations. Everything is fine because now it is in the echelon form. So you got the principal diagonal elements. Below that there is only 1 0 because it's only up to order 2 by 2. So now what is elimination is done by row elementary operation. So what do you mean by back substitution now? Actually, you will start with here from the bottom. So here you go 13. On the right hand side you go minus 26. What's the meaning? This column is now nothing but the coefficient of Z or X2 here. According to this problem, X1, X2. So this is coefficient of X2. So 13 into X2. So this is what exactly means. So it shows automatically 13 into X2 equal to minus 26. Okay. Therefore, X2 is equal to minus 2. Right. Next you write, then you are having this equation. And next you are having this equation. After this only, this equation, that is you are going here 2x1 plus 5x2 equal to 2. So in which you substitute for x2 equal to minus 2. So 2x1 is plus that is minus 10, 5 into minus 2. 2x1 minus 10 equal to 12. So 2x1 equal to, 2x1 minus 10 equal to 2. So 2x1 equal to 12. Therefore x1 equal to 6. Thus you are having x2 equal to minus 2. X1 equal to 6. Better, always you can finally write the solution in that order. In that order means, therefore, the solution is x1 equal to, always we write first component first, second component next. X1 equal to 6 and x2 is equal to -2. And you know very well always, whenever you find a solution, it's better you check in any one of the equations, even all of it is very easy to check. You don't need to show. Even if you show the checking, nothing wrong in it. You can see for yourself. See, take the first equation 2 into 6, 12, plus 5 into -2, 12 minus 10, 2. Left hand side equal to right hand side. So the equation is satisfied by the values of x1 and x2. So they become the solution. Take the second one. It should be true for every equation of the system. -4 into 6, -24, plus 3 into -2, -6, -30. Correct. Okay. Right. So this is now a 3 by 3 matrix. Now, shall we take it up after 5 minutes break? The same thing
Sure, sir.
we're going to do. Okay. Shall we break for 5 minutes if you want? Otherwise, we'll complete this and then go for break. What do we do? We'll go for a break for 5 minutes? Okay.
Yeah, sir.
Yeah.
No issues.
Okay. Right. Hello. Let me resume the class. Hello.
Yeah, yes.
Oh, okay, good. Now let's just look at. We go for solving a system of three equations in three unknowns. Solve by Gauss elimination method the following equations: 6x1 plus 2x2 plus 8x3 equal to 26, 3x1 plus 5x2 plus 2x3 equal to 8, and 8x2 plus 2x3 equal to -7. That means 0x1 plus, isn't it? When there is no coefficient means, when there is no variable means its coefficient is 0. It's understood. Okay. Now take the augmented matrix. Matrix of coefficients, column vector 6, 2, 8, 3, 5, 2, 0, 8, 2. That's important. Okay. So the first column, coefficients of x1 are 6, 3, 0. Second column, coefficients of x2, 2, 5, 8. And third column, coefficients of x3, 8, 2, 2. The constant column vector 26, 8, -7. Now, what do we do? Keep the first row intact. Okay. So 6, 2, 8, 26. Always keep the first row intact. Now, in general, okay, supposing you are having a zero element in the first row, and especially you are asked to do by partial pivoting method, of course, same Gauss elimination, it lays some emphasis on a kind of interchange of rows, because even before we resort to taking up partial pivoting, if you find zero in the first row, first column element, that is especially first column, you need to interchange the rows, that row with any other row where you have a non-zero constant. That is very, very important. Okay, right. Therefore, here there is no problem. So you just go about. Keep R1 fixed. So actually, as I have just shown you in the last problem, R1, arrow mark R1. That is one way of writing. Or you will just write R1, that is R1 is kept as it is. Now, R2, arrow mark, then you write the transformation. Means the new R2 is obtained by performing this row elementary operation of R2 on R1, because R1 is fixed. So what is the elementary row operation you need to do? You should always think of making the first column second row element to be 0. Okay, that is the first step. So what do you do here? Here you have 3, here you have 6. There are two ways of doing this: 2 into R2 minus R1. You can say 6 minus 6. Anyway, this is made to be 0. So 2 times 3 minus 6, or 3 minus 6 into 0.5. What I would understand. So here, of course, this author has written that way. The new R2 is obtained by taking the existing R2 addition minus 0.5. That is, we are subtracting R1 multiplied by 0.5 or half. So what is happening? 3 minus 6 into half. 3 minus 3, 0. 5 minus 2 into half. 5 minus 1, 4. 2 minus 8 into half. 2 minus 4 minus 2. And it should be done throughout. Don't forget to do the elementary row operation on the right hand side also. That is, complete augmented matrix must be taken into consideration for the operations. So 8 minus 26 into half, 8 minus 13 minus 5. So that is your new R2. Now, as usual, you know very well, here one step is next. Okay, what is the next step? One set of elementary row operations you will do one after another in one step itself. That is one set of, we'd say one set of operation. That is R2 in terms of R1 in order to make R2 first column element to be 0. Similarly, R3 first column element should also be made 0. So you have to make on R1 again another set of elementary row operations. But in this problem, it so happened you are already having 0. Then you may ask one question. Here it is given R3 plus minus 0 into R1. So that is not necessary because we are going to, already it is 0. So there is no point in just multiplying by 0 and then subtracting. You don't need to. Anyway, just for understanding it is shown. But remember, since it's already 0, no operation is required. So it will be as it is 0, 8 to minus 1, which means that this second set of operations of R3 on R1 only to in order to make the first column third row element to be 0 is now is not required in this problem because it's already 0. Okay, understood? Is it clear here?
Yep, sir.
Is it clear?
Yeah.
Right, fine. So one step is saved. So go to the next step. Now R2 is fixed because already R1 on which R2 and R3 are done. R3 is of course the same because already 0 is there. Now we need to do, we have to go for now third row and second column. So this must be this element. Your third row, second column element must be made 0. Isn't that? Then only you will have zeros beneath the principal diagonal element so that it becomes upper triangular. So you need to do R3, operation on R3, but this time don't go to R1 because already R1 is used, isn't it? Therefore keep R2 because R2 is now leveled, R2 is stabilized, R2 is fixed. So keeping R2 fixed, do operation of R3 on R2. Well, so what is to be done? You are having 8, you have 4. So as I said just before, either you can write 8 minus 2 into 4, or this is, yeah, that will be easy because you can write this is bigger number, isn't it? So R3, new R3 is obtained as R3, existing R3 because this is already 0. So R3 8 minus 2 into 4. You should only see the how you are getting 0 between these two elements, which is to be generalized throughout the R3 in terms of R2. So 8 minus 2 into 4, which means whole of R3 minus 2 times R2. You can check, of course, there should not be any change by doing this kind of elementary operation, which already has been which on the first column, in the first column of second row and third row, which are already 0, already have been made. If you are making any operation here wrongly, definitely it will create a non-zero entry here, which is wrong. Isn't it? Therefore, you must ensure that. So you can check now 0 minus 2 into 0. So there is no change. This is now becoming 0. So correspondingly, 2 minus 2 into 2, isn't it? 2 minus 2. 2 minus, so 2 plus 4 now. Oh, sorry, no, it is 2 minus 2 minus, there is 2, you are having third row, and second row means minus something wrong, 2 minus what is that? They have made some interchange. That's why it's not necessary. So here, that's what I'm wondering. Here it is 0, 4 minus 2 minus 5. Here it is 0, 8, 2 minus 7. Okay. So they have written here 0, 8, 2 minus 7 R2. And then they have gone for interchange of, they have gone for row elementary operation of this, keeping as R3 in terms of this R2, which is not required. It is not at all required. You can keep as it is. You will still get the corresponding answer. I don't know why it has been done here. It is not at all required. Have you got it? They have changed 0
Yeah,
into -7 to be R2, and this is R3, and then performance of R3 on R2 is done, which is not required. Unless there is something important. That is, as I said earlier, in the very first row, if there is any 0, you have to interchange, but not here. It's not necessary because you need to make this a 0. So keep this -2 times this. There is, it's not required. Therefore, anyway, they have interchanged and then done this operation to obtain this way. So you can cross check your own way. Okay. I just leave it to you. You will get the same answer. So you get, but not this 0, 0, -3. You will get rather 2 -2 into -2, 2 plus 4, you will get 6 here. And therefore, correspondingly here, -7 here, plus 10. So -3 you will get. So what you will get then? 6x2, 6x3 is equal to 3. Therefore, x2 is equal to x3 is equal to half. Same thing. Is it right? So putting x2 equal to half from this 8x1 plus 2x2 equal to -7, you get x2 value. And then from this, you will get, after substituting values for x1, x2 and x3, x1 value. So this is what in general we do by Gauss elimination method in which we have a forward elimination, backward substitution. Here, well, there is one more extra. The term is added here. So unique solution. Of course, whatever we have found in the previous problem also, it was unique in the sense in this problem, x3 equal to half, x2 is equal to -1, and x1 equal to 4. Well, finally you write. Therefore, the solution is in the order of x1, x2, x3, and so on. So x1 is 4, x2 equal to -1, x3 equal to half. Since it is back substitution, you will definitely have the last component of the vector, the first one, the second, that the first is the last. But you write it in the order, first one, second one, third one. That is the way we have to write the solution. Anyway, it is the unique solution. So anyway, here in this problem, something is just underlined in the sense that if at all you are asked to find whether the solution is unique, automatically the solution that you are obtaining will definitely show that it is unique. Okay, which of course, if at all want to be cross-checked, then you have to have, because by the way the solution is there, the system is consistent. Since it is unique, definitely it is going to tell you back that R of A is equal to R of AB equal to 3, since there are 3 unknowns. Isn't that? So this is a similar kind of problem. You have 2, 1, 1, 8, -3, -1, 2, -11, -2, 1, 2, -3, and so on. So keeping R1 fixed. So look at the first row, first column element, it is to be non-zero. That is very, very important. If it is 0, interchange with any of the 2 other rows. Then you may have one doubt. If there are also zeros, it will not be there. Definitely it will not be like that. Definitely there will be at least one row in which there will be non-zero in the very first column itself. Okay. Then only we can go about using this Gauss elimination. So that you ensures here it is fine. So keep R1 fixed. So here it is not written R1. That means R1 is fixed. So we have done in the first set. So here you just see that you are doing, it is -3, it is -2. So here you have in the very first step itself 2 kinds of operations. One of R2 on R1, another of R3 on R1. R1 only. Don't be misled. R1, when you do R2 in terms of R1, don't do R3 in terms of R2, because R2 is just now have come into picture. So R1 is only fixed in the very first set of 2 operations. So R3 is also in terms of R1 only. Once this set is completed, when you go for the next set, you need to do only one operation when it is of order 3 by 3. And this time you are going to have only elementary operation of R3 based on R2 only, because R2 is now fixed. Okay, right. So you have back substitution, and you just look at here, -1, here 1, which means minus z equal to 1 here, because here the problem is having unknowns x, y, z. So minus z equal to 1, which means z equal to -1. Okay, then half into y plus half into z equal to 1. Therefore, you have putting z equal to -1, y equal to 3. Then 2x plus y minus z equal to 8. So substituting for z equal -1, y equal to 3, you get x equal to 2. That's as it is, as I just now mentioned that you write the solution set in the order of variables x, y, and z, or x1, x2, x3 in that order. Well, here there is yet another example where there is no solution. So here you are asked to solve by Gauss elimination method, isn't it? Only when you are doing the operations, you are going in the process, you are able to understand that there is no solution. So when the question is, in general, mostly whenever you are asked to solve by Gauss elimination method using in general or by partial pivoting, definitely there will be a solution, and that too unique. But sometimes you may end up with infinitely many solutions or no solution also. So that only when you do the process, you will be able to understand. So here, as we go about, so here is an example for no solution, which you are able to see yourself at the end. How? Let us see. So you are keeping R1 fixed, R2 in terms of R3, R3 in terms of R1. Then in the next set, R3 in terms of R2. So you are end up with, look at the last, after two sets of operations, 3, 2, 1, 3, 0 minus of 1 by 3 minus 2, 0, 0, 0, 12. See, it so happened when you are doing the second set of operations of R3 in terms of R2, it has come on its own automatically because of the operation. This also 0. That is third column, third row, coefficient of Z is also 0, which we have not done. When you do the set of operations, it comes on its own. Therefore, what you understand by back substitution, what we are supposed to do. So it shows that actually 0 z is equal to 12. Minus 1 by 3 x2, x1, x2, x3. So 0 x3 equal to 12. Minus 1 by 3 x2 plus 1 by 3 x3 is equal to minus 2. 3x1 plus 2x2 plus x3 equal to 3. So here, by just looking at this, don't jump to the conclusion z equal to 0, that is x3 equal to 0. No, the coefficient of the variable itself is not there. Means there is no solution. That's the meaning. Because if you just look at this, it shows what? 0 z equal to 12. Isn't it? 0 z or 0 x3 equal to 12. So in the previous problem, you had some 2x3 equal to 2, some x3 equal to 1. But here 0x3 is equal to 2 because the coefficient is 0. So which doesn't mean that the x3 equal to 0. Okay. This means actually if you are so serious about, then you will have say 12 by 0, x3 equal to, isn't that? There is no solution.
Correct. Yeah.
Okay. Therefore, you have to be careful. This is a false statement. So that the system has no solution. So in this problem, if at all you want to have some kind of cross-checking that you have understood previous things, that if you find rank, consistency will not be there. There is no solution. So definitely rank of A will not be equal to rank of AB, which you can check, which you don't need to show here, but you can. So that is yet another. Yeah, in all the problems you are starting, you are going by Gauss elimination method, but then it's not necessary that you will end up with a unique solution only. You can have no solution as in the previous problem. And as you are going to see that repeated solution, in other words, infinitely many solutions. How is that? You just see that. Here, of course, you have a homogeneous system because on the right hand side, you have the constants are all zeros. Okay. So let us just find away, all those things now. You just see here, we end up with 1, 2, minus 1, 0, 0, 2, minus 3, 0, 0, 0, 0, 0. What's meaning here? 0 Z equal to 0. So the coefficient of Z is 0 means we should not say immediately here. Actually, there is no solution because if you go further, Z is free. See, Z there is the coefficient of Z is 0 means here you don't have any value because you look at the right hand side. 0 Z equal to 0 means Z equal to, don't say 0 by 0. 0 by 0 is indeterminate. So anything you put for Z, you will get the equation satisfied. 0 into 1, 0, 0 into 2, 0, 0 into 3, 0. So in general, let Z equal to some t. So when you go back, 2y plus 3z equal to 0. So y will be equal to, here you get minus 3 by 2 t when z equal to t. Similarly, x equal to z minus 2y, x equal to 40. So x equal to 40, y equal to minus 3 by 2 t, z equal to t. So whatever value you give to t, don't give 0 because if you give 0, you get trivial solution. Any non-zero value, you get corresponding values of y and x so that you will be able to generate as many solutions as possible. Okay. So you are getting infinitely many solutions. For example, he says here 1 in particular is 8 minus 3, 2. Supposing z equal to 2, you get minus 3 by 2 into 2 minus 3. Here you go 4 into 2, 8. This is one of these many solutions. So this is yet another example where you will come across a unique solution, no solution, and infinitely many solutions. These are all possible. Well, now before we go for further phase of solving system of linear equations by Gauss elimination, especially using pivot, partial pivoting in particular. Before that, we just go about having some kind of idea about norm. Norm is nothing but something like your absolute value, but it has its own definition. Just see that its magnitude in general. A vector norm for column vector x equal to xa with n components, x1, x2, x2, xn is a generalized length. So length, it's nothing but a length, a magnitude denoted by. So for absolute value, you put x within two parallel lines, and for norm, you will put between two parallel lines on either side. Okay, that stands for norm. And what are its properties? Norm x is a non-negative real number that is greater than or equal to 0. It cannot be negative. It can even be 0. When it will be 0? Only if x equal to 0. Only when x equal to 0, norm x is 0. That is norm 0 equal to 0. Okay. So for all positive numbers, you have a positive real number. Norm kx, where k is a scalar, it will be equal to modulus of the scalar into norm x for all k. Norm of x plus y less than or equal to norm x plus norm y. Triangular inequality. This much you might have heard about. So very, very famous inequality in norm known as triangular inequality. Norm x plus y less than or equal to norm x plus norm y. Well, this is true for absolute value also. Modulus of x plus y less than or equal to mod x plus mod y. Okay. Matrix norm. So if you take matrix, its norm corresponding to given vector is defined by norm of the matrix A is maximum of norm of AX is multiplication of matrix with the vector by norm x. Okay. So just an observation, that's all. Now here, matrix norm. Again, here we are going to have some specialization by putting some subscript and giving an appropriate definition. Norm of a matrix measures maximum stretching a matrix done due to any vector in the given vector norm. So matrix norm corresponding to vector 1 norm is a maximum absolute column sum. Vector 1 norm means norm A suffix 1. When you put one norm suffix 1. What is the meaning? Maximum of summation of absolute values. Maximum of sum of absolute values of the column elements. So you find the sum of, supposing you have a 3 by 3 matrix A, A11, A12, A13 first column, A12, A2, 2, A2, A3, 2 is your second column. And then A1, 3, A2, 3, A3, 3 is your third column. So you will find sum of each column and take absolute values. Absolute values of sum of absolute values of each column and then take the sum. And that's you take the maximum. So column sum, absolute column sum, that is modulus Aij, summation over A equal to 1, maximum over J. That is called a norm, vector 1 norm, matrix norm corresponding to vector 1 norm, matrix norm corresponding to vector infinity norm. Okay, just a notation. So we don't go to that infinity concept here. So vector infinity norm here is maximum. Same way, absolute row sum, absolute column sum maximum, norm A1, that is matrix norm corresponding to vector 1 norm. And matrix norm corresponding to vector infinity norm is maximum, absolute row sum. So norm suffix infinity, norm A infinity equal to maximum over I, summation modulus Aij, j equal 1 to n. And norm A suffix 2 can also be referred to as norm A suffix f because it was named after Frobenius. So he invented this norm and it is named after him, Frobenius. That's why it is having the first letter f. So when you have the vector 2 norm, then it is suffix, it is denoted by norm A suffix 2 or norm A suffix f, which is nothing bad. You have summation and modulus of Aij square. So column and row absolute values product and then double summation. So double summation I equal 1 to m, summation j equal 1 to n, modulus Aij square. Condition number definition. Condition number of square non-singular matrix means determinant A not equal to 0. A matrix is said to be non-singular if its determinant is non-zero. Condition number of square non-singular matrix A defined by COND, that is condition of A equal to norm A into norm A inverse. That is condition number of a non-singular matrix is product of the norms of A and its inverse. So by convention, condition of A is infinity if A is singular naturally. Because norm, what is A inverse? 1 by determinant A into adjoint A. When it is singular, determinant A will be 0, 0 will be in the denominator. That means we get infinity. So condition number of A will be infinity naturally for a singular matrix. Okay. So let us just take an example. Let A be equal to 2 minus 1, 1, 1, 0, 1, 3 minus 1, 4. Norm A suffix 1, that is find matrix norm corresponding to vector 1 norm, means norm A suffix 1. Okay. What is the answer? Take a column sum. Absolute values you take first, then column sum. Okay, take first column. Everything is positive. 2 plus 1 plus 3, 6. Take the second. Take absolute values of the second column. 1, modulus of minus 1, 1 plus 0 plus 1. It's only 2. Go to the third column. You don't need to take absolute value because already they are positive. 1 plus 1 plus 1, 4, 6. So which is maximum? Maximum of column sum. 6. That is your norm A suffix 1. What is norm A suffix infinity? Row sum. Maximum. Take the first row. Take absolute value. That is very important. Absolute row sum. That means sum of absolute values of each row. 2 plus 1 plus 1, 4. 1 plus 1, second row, 2. And go to the third row, 3 plus 1 plus 4. Don't say minus 1. Take absolute value and then 10. Take sum. Modulus 3, that is 3. Modulus minus 1, 1. Modulus 4, of course, 4. 3 plus 1 plus 4, 8. So norm A suffix A infinity is 8. Okay. A inverse, of course, it is found here because it's a big, that itself is a big problem of finding determinant A and then 1 by determinant A to adjoint A and its values are given. So we will find out now norm A inverse suffix 1. Go for column sums, absolute value after taking absolute values. 0.5 plus 0.5 plus 0.5, 1.5. Second column, 1.5 plus 2.5 minus 0.5, that is 3.5. Last column, 0.5, 0.5, 0.5, 1.5. So 3.5 is the answer. So sorry, 4, it's not minus 0.5, absolute value. So 1.5 plus 2.5 plus 0.5, 4.5. So norm A suffix 1 is 4.5. So norm A inverse suffix 1 is 4.5 from A inverse matrix. Norm A inverse suffix infinity, take row sum. 0.5 plus 1.5 plus 0.5, that is 2.5. This one 2.5, 3.5. This is 1.5. So 3.5 is your norm A inverse infinity, isn't it? Well, we have found norm A 1, norm A infinity, norm A inverse 1, norm A inverse suffix infinity. What is condition of A? Condition suffix 1 we can put for now when you are calculating norm A inverse with respect to 1 norm, isn't it? 6 into 4.5, that is 27. Condition suffix infinity of A is norm A suffix infinity into norm A inverse suffix infinity, that is 8 into 3.5, 28. Techniques for improving the solution. Pivoting techniques. If a pivot element is 0, normalization step leads to division by 0, which is not possible, in the sense which is not correct because it will lead to infinity, isn't it? Therefore, this problem when arises can be resolved by the following procedure. See, either it is 0 itself or close to 0 anyway. In practical problem, it will be 0 only given. Is it R 0.000? Anyway, it is close to 0. In that sense, it is given. See, close to 0 means not in the limiting sense. It is 0.00000 some 1, which means close to 0. Is it right? So whether it is exactly 0 or close to 0, you cannot divide by 0. So the pivot element row should be interchanged, so as to make the first row, first column element should be a non-zero element. So there are, in fact, 3 techniques, types of techniques called partial pivoting, complete pivoting, scaling. Well, we don't, according to your syllabus, we don't go deep into, we don't go at all complete pivoting and scaling. Just for namesake, we just have listed that partial pivoting, complete pivoting, and scaling. So what is partial pivoting? Switching the rows below so that the largest element is the pivot element. Look at that. That's very important. Okay. Even look at the term largest. Even if there is if there is 0 in the first row first column element, definitely you have to interchange. There is no doubt about it. But even if it is non-zero in the first row, unlike general method of Gauss elimination, when you go for pivoting technique, partially, as we are going to concentrate only partial pivoting, you need to consider only that row column which is having the largest element. Of course, we will start with the first column. That is what we are giving importance to, the partial pivoting. What is complete pivoting? Searching for the largest element in all rows and columns, then switching. This is rarely used because switching columns changes the order of access and adds significant complexity and overhead costly. Therefore, we don't resort to complete pivoting at all. Scaling used to reduce the round off errors and improve accuracy. Anyway, we will not be resorting to these two. We will be concentrating on partial pivoting, which is of great interest. Just look at. I give you a good example where the problem is to solve Gaussian elimination method by partial pivoting. Therefore, remember, if in the question paper you are asked to solve by Gauss elimination method without searching for largest element and making changes in the pivot, only condition that for elimination in general, the first row, first column element should be non-zero. If it is 0, naturally you have to interchange. But even if it is non-zero, But for partial pivoting technique, when you are using, you are asked to use, if you are asked to solve the system of equations by Gaussian elimination, partial pivoting method, then you need to look forward to largest element of the first column. If it is not readily available in the first column in the question itself, then you have to interchange the rows. Then you have to go about as before. Okay, right. Now you take the augmented matrix. Okay, you are given system of linear equations, three unknown, three equations in three unknowns as usual. Now write the given system in augmented matrix form. You know very well. You have, of course, the left hand is cut. Better we will write now here. It is 1, left hand is 1. It is here -3. And here it is, you have 2, isn't it? Yeah, I will write separately. Yes, we can. 1 -1 1 -3 2 -3 2 -5 4. Just put your demarcating line. 1 -6. Okay. This, of course, I don't want to. That's for understanding. Here, of course, you have 2 here. Anyway, okay, I just made it very clear. So you have the augmented matrix, you know very well. Now, okay, up to this, you know very well. Then just to see here, from the first column with the non-zero components called the pivot column, select the component with the largest absolute value. Look at this. Largest absolute value. That is important. Not only largest, but absolute. Because if you take, for example, you have 1, you have -3, you have 2. 2 is bigger. 2 is the largest. But if you take absolute values, this is 1, this is 3, isn't that? And this is 2. So which one is now largest? Modulus of -3, which is 3. Therefore, here, again. So rearrange the rows. You just look at. To move the pivot element to the top of first column. So here, this is the pivot. That is absolute value. If you take absolute value, it is the largest, but don't put my +3. Whatever element is there, that is to be taken. So you are now interchanging. So rearrange the rows to move the pivot element to the top of first column. In the sense, here we are rearranging. Just look at here, interchanging. We are interchanging. So what's happening here? Interchange. That is R1. If I put two-way arrow mark, it is interchanging. Isn't that? Here. So you have 3 here. It coming. It is -3 actually. It is minus 3. First row is 1 minus 1 1 and third row is 2. Okay, that is missing. So 3 2 minus 3 minus 6 is just brought forward to the first row, and first column element is the largest of the first column. That is the pivot element. So your minus 3 is now the pivot element. Okay, so of course there are two types of methodology here. Some authors take the pivot element as they are and then go by, as usual, elementary row operation and do the same thing for the second column and then third column and then as usual. But some authors do make the pivot as 1. Make the pivot as 1. That is also permissible. Some authors follow this. That is good. So what we do now, we just do the same thing here. So in order to make this pivot, this is the pivot element now. This is your pivot element. This is your pivot. So by partial pivoting, we are bringing the largest of the first column as the pivot element, and is to be repeated for the second column and third column while we are doing the elementary row operations as and when required. I mean, in the successive steps. So minus 3. So as I just mentioned, you can have it as it is, or better, according to this way of doing, you can divide it by that number so as to make the pivot 1. Just a minute, I'll just plug in. So what's happening? Let's follow this. So what will happen? Minus 3, that's what's written here. We now do only rearranging the rows. Which row? The row in which, of course, the column is very important. First column is the pivot column. And in the pivot column, it so happened in this problem. First, if you look at, you have elements 1, minus 3, 2. And if you take absolute values, minus 3, modulus of minus 3, 3 is the largest. Therefore, that row is to be made to be the first column, first row. So that element will become the minus 3, not plus 3. The element that is available there becomes the pivot element. And the column is pivot column. Okay. So we will make it as 1. Okay. Just for simplification purpose, that's nothing more. So you have now divide by R1 divided by minus 3. So you have, it is 1 is 1. And here it is 1 by minus 1 by 3. Sorry. Minus 1 by 3. This again I will explain in the next class. Okay. So I will put another so by 3. And the last one is again minus 1 by 3. Isn't it? And that is 2 actually. It's 2, isn't it? Yes. Minus 2 by 3. Last element, first row, first column. I will make necessary corrections and then upload in the Teams for your proper reference. Okay. So this becomes minus 2 by 3. Then, no, sorry, only the, only the first row, because only pivot element is to be made 1. So not thrown by, but sorry, this is, it's not right. Other elements will remain the same. That is, only that is to be made before we go for elementary row operations. We just make it convenient, that's all. This is now 1, Easy to perform element row operation. That's all. 1. This is now 2. Okay, right. Now, understood? Hello? Is it
Yes,
clear?
sir.
Okay, right. So next, if you go. So what's happening? Well, we are having now add multiples of the first row to the other rows to make all other components to the pivot column equal to 0. That is, this is nothing but elementary row operation. That is, we are performing, that is performing elementary row operations. So R1 is kept fixed, R1 is R1 as usual. We will now perform as usual elementary row operation. R1 is R1 itself as before, as usual. So you have 1 minus 2 by 3, 1, 2. Okay, this is only demarcating line. So don't be misled this one. This is actually demarcating line. Okay, even in the previous one, don't take this as 1. This is actually, so this is clear. Augmented matrix line. Okay, right. So you have R2 minus R1 because here you had 1. You just go back. You had 1 here. You need to make this second row, first column to be 0 as before, as usual. So this is easy now. 1 minus 1, 0. So R2, newly obtained R2 is nothing but R2 minus R1. So you have this kind of simplification, this kind of simplification. Now you should go to second column. In the second column, take absolute values. 2 by 3, 1 by 3, 11 by 3. Which is the largest? Which is the largest? 11 by 3 is the largest, isn't it?
In absolute terms.
Absolute, yeah. Everything, absolute. Absolutely. You are right. Absolutely, absolute. Absolute mod minus 11 by is maximum. I will put it simply.
Yeah. Yes.
That's all. So that is now rearranged now. New pivot. See, it's shown here. New pivot. But now we are doing second set. Therefore, this has to go to second row now. Isn't it? So we have to now rearrange between third and second rows. First rearrange, then we go for division, then we go for performance. Let's see. R3 and R2 are interchanged. So that your minus 11 by 3, the new pivot is occupying your second row, second column. It should be in that order. Same thing. Once that is done, suppose automatically in the performance it is there. That is the largest in the second row. Just leave it. No interchange. We just ensure it that it is the largest after taking absolute value. And it is, if it is there already in the second row, well and good. If it's not there, you cannot go back to R1 now. Only you have to interchange with the R3. That's all. Now, again, R3 is divided by minus 11 by 3. It's not R3. It should be R2. There is a mistake in the print. It should be only R2 because now it is in R2, isn't it? R2 is divided by minus 11 by 3 to make the pivot as 1. Just see that. The pivot as 1. That's all. So R1 is fixed, R2 is fixed. Go for R3 in order to make this as 0. Is it right? So we are doing R3. So these 2 or 3 steps we have not done in our general Gauss elimination process. Here we have been doing an extra pivoting. So now, as usual, in the first set itself, only one operation is done. Then we rearranged. Then we ensured that pivot is made 1. Now we go for R3 in terms of R2. So in order to make this as 0. That's it. So now the last one, we have got now third row, third minus 2 by 11. You have 1 is there. Minus 6 by 11, if you take absolute value, it is 5. So this is again here again by R3, you are interchanging now actually, isn't it? Because this is bigger. This is bigger. Modulus. It is modulus of minus 6/11 is maximum, and therefore we are interchanging. After interchanging, we find that first row is fixed 1 minus 2/3 1 2. Second is 0 1 minus 6/11 minus 3/11. Oh, this is already done, isn't it? So we don't need to worry about this. Okay, okay. So we are only bothered about now the third one that is now made to be divided by 1. So this is already done. So we don't need to change. We don't need to change. It's already done. Yeah. So new pivot is only now automatically it is there in the third row. So we have already done two operations of finding one new pivot in the first column, first row, and in the third column in the second row. And then now we are left with only the last one. That is the new pivot minus 2/11 divided by new pivot. So you get these things, isn't it? Then that's all. Now everything is in our proper order. So your Z or X3 equal to 6. X2 minus 6/11 X3 equal to minus 3/11. So that X2 is 3. And X1 minus 2/3 X2 plus X3 is equal to 2. Substituting the values of X2 equal to 3 and X3 equal to 6. Back substitution, X1 equal to 2. Thus the solution is therefore X1 is equal to 2. So X2 is equal to 3 and X3 is equal to 6. This you can of course check with any one of the equations by putting in the left hand side and ensuring that it is equal to right hand side. That's what it's given. So the solution is, it's already there. X1 equal to minus 2, X1 equal to minus 2. Sorry. X1 equal to minus 2. X1 equal to minus 2. X2 equal to 3. X3 equal to 6. So check it. It's there. Okay. So this method fails if the element in the top of the first column is 0. Therefore, in this case, we can interchange the rows so that the pivot element in the top is brought to the top of the first column. So I think we have a similar problem. Partial pivoting, example 2, 4 equations in 4 unknowns. So if you are asked to use partial pivoting, then definitely you have to go for this pivoting method. Otherwise, you can generally go for front elimination and back substitution. Well, hope you would have understood. If you got any doubt, you can ask. Otherwise, I will stop sharing and end the meeting. Okay, AR, got it? Is it clear?
Fine, sir.
Okay, fine, good. Fine. Thank you. Thank you for your rapt attention throughout the session. And what's your full name?
Apurv Ranjan, sir.
Good. Okay. Thank you. Capital.
Yeah. Thank you, sir. Thanks for
Thank
sharing
you.
the knowledge.
Thank you.
Thanks.
Thank you.
Have a great weekend, sir. Thanks.
Thank
Bye.
you. Same to you.